Hello, everyone. My name is Dennis, and I'm the Chief Security Officer of My Network. My Network is an FHE layer for AI and POS networks. And today I will share the voting mechanism, the voting infrastructure of the My Network. And the product name is called MindV. It's actually an application of the FHE. And it provides it actually contribute to the secure of the consensus of AI and the POS networks. At the beginning, I would first briefly introduce the concept of the citizen Z. We can also call it a citizen zero trust. This is actually a concept proposed by us, My Network, and other FHE pioneers, such as Zama, Inco, and Phoenix. And the main purpose of it is to enable their personal autonomy in the digital world. It aims to protect each individual's assets and transactions and votings and other behaviors in the digital world by encryption. And today, let's dive into the voting topic, and let's see how to implement a fair voting mechanism, and how does it contribute to the secure of the consensus of AI and POS networks. First, needless to say, voting is very important, and maybe one of the most important mechanism in human world. Last week, we already witnessed a big event of this year. It's the US election. Maybe the whole world will be influenced by the voting results of the US people. And also in technology world, voting is also important. We often use, for example, DAO for the governors of Web3 communities, and we can also use DAO to set the parameters of Web3 protocols. And besides, for the governors, we can also use voting in some automated processes. For example, the election of blocks, the election of the validators. So voting is also important in the technology world. Let's take one step back. Let's have a look how do we do the voting in traditional way. In traditional approaches, actually there would be an authority. It's usually called something like the voting committee, and every participant, they have to trust this authority, because they just send their votes to this authority, and this authority, he is responsible for collecting the votes and do the computation and generates the final result. And this one has to be trusted. And because they have no other choice, and this mechanism has worked for maybe hundreds of years, and sometimes it works well, and sometimes not. Actually, that depends how this committee did his job. Because if he wants to do something bad, and the voting would be not fair. So to improve this process, we designed this, we launched this product called MindV. And you can take a quick look at this complicated architect, and I want to dive into the details into it, and let's go to the simple principles. We have three simple principles for a fair voting. We think the voting requires accountability, transparency, and privacy to become fair. And let's first talk about the accountability. Because for a voting process, for a voting mechanism, the accountability is actually very important because each voter, they have to be responsible for their own votes. If the voting result is not related to each one's own benefit, and they won't care about the voting, and they just generate some kind of the random votes, and the final voting result would also be some random meaningless result. So accountability is important. And how can we to ensure this accountability? In Web3 world, we actually are very familiar with this. We often use incentives, use slashes, so that if the voters he doesn't do the good job, he will be punished. And if he did his job, he will be rewarded. So in MindV, in the product, we just designed this part for the incentive. We use a token which is called a FHE, and this token is actually represents the voting power. And if a user he wants to get his voting power, he will stake in do the stake in the staking pool. He can directly staking into our Mind's staking pool. He can also stake into our staking partner's staking pool. And during the process of his staking, he will continuously get the VFHE from Mind, and that represents his voting power. And he can use this VFHE to do the voting. He can directly vote for himself, and he can delegate his voting power to others and let others to vote for him. And he will get the reward from the direct voting or the delegation. And this is the incentive mechanism, and this ensures the accountability of the voting mechanism. And the second principle is transparency. Transparency is actually needless to say very important for voting, and it's actually not a very difficult principle to implement in the Web3 world, because blockchain is actually completely transparent. All the data on the blockchain, everyone can access the data on the chain. So in our product of MindV, we just used a normal EVM chain. It's actually no different with other blockchain. We just launched a normal EVM chain, and its purpose is mainly for the voting purpose. And this is to ensure the transparency, because we can just make sure that all the voters, they send their votes to the chain, and the whole process would be transparent. And until now, we have accountability and transparency. Actually, we have, in the Web3 world, we already have many successful cases who did this quite well. And the DAO, I already mentioned before, and the BitTensor, it is a very successful AI project who also relies on the voting mechanism for the miners to generate the parameters for AI network, and the validators, they will validate the result. And that's also on the blockchain, and so that turns into a successful AI network. However, they are not perfect. They are very successful, but they have some kind of the issues. That's privacy. Because let's think about it. In the first principle, we already have the accountability. This means that the voters, they are driven by they are motivated by the profits. And in this way, they have also the motivation to cheat in the voting process, because they are trying to get the most benefit from the voting, and in their voting process, they can take some strategy like copy others. For example, they can copy the votes from the big whales, because all the votes, they are on the blockchain, and they will get the direct access to the plain text. They can just copy their votes, and in that way, they will get more profit from their voting process. To get rid of it, we have to design some kind of the mechanism to prevent the voters know each other's votes. That's not a difficult process. This principle alone is not difficult, because we can use encryption. As long as the votes are encrypted, the voters, they won't be able to get access to each other's votes. However, if we do the encryption and it turns back to the traditional votes, if all the votes, they are encrypted, and the voters, they do not do the whole process, and then again, only the authority is able to know the votes and generate the final result. So there should be some balance between privacy and the transparency. These two things are some kind of contradict to each other. If we have complete privacy, and surely they won't be transparent again. If we have, for example, in the right picture is just something like the DAO. We just send votes to the chain and then generate the result. This is completely transparent. However, this will encounter the problem I just mentioned, that they can cheat. They can copy the vote of other users. So our choice is to implement the delayed transparency. This means the transparency can be ensured after the reward is distributed, after the voting result is computed. So this means we have to do the computation on the ciphertext, and at this point, FHE is required. FHE is the privacy computing, and the one who is responsible for doing the computation, he don't have to know the real information of the plain text. He just got the ciphertext from each voters and do the computation over the ciphertext and generate the encrypted result. He has completely no idea what's in the voting, what the real information of the votes. But he will be able to generate the result. And then the result can be decrypted, and the voting result can be published. After that, the whole voting process can be decrypted. If someone doubt about the result, and then the votes, the results can all be decrypted, and to do the validation whether the voting process acts in a good way. Yeah, and then the process becomes this way. The voters, they send the encrypted result to a network, which is called FCN. FCN is the FHE consensus network. Why we require a consensus network here? Because just in the last session, as Sean said, for FHE, we have to validate its result. That's the integrity issue of FHE. If I only have one single node to do the computation, and no one can make sure that he did it in a correct way. So we use a network to make sure of that. We have different nodes to do the same computation, and then they get the result. They just send the result to the chain and get the consensus on the blockchain. So that is the FHE consensus network. It is responsible to collect the encrypted votes from the voters, and then it will do the computation and generate the encrypted voting result. And this encrypted voting result would be sent to a network called FDN. It is FHE decryption network, and it is responsible to decrypt the voting result and then release it to the public. And if someone doubts about the voting process, FDN can also perform the decryption for the votes for the original votes. So we will then get the results in plain text and the original votes in plain text, and we can just verify whether this vote process is fair and it works properly. Okay, we already have the trial of accountability, transparency, and privacy. And here, at this point, we can do something to make this product work more efficiently to increase its flexibility. We actually made the product of MindV. It's actually at a layer, at an application layer. It is called Hub. So this means that the developers, they will be able to use the Mind SDK, and it will be able to use the resource of the FCN, FDN, and they can design the application for themselves for different scenario and different purpose of their voting. And they write the contracts and the computation logic and make it something we call the hub. They can just deploy the hub and make use of our voting infrastructure for their voting scenario. And then let's go back to the complicated architect. In the left side, that's for the incentive purpose. That's the users, they just use restaking. They directly restake into the Mind protocol, or they can restake our restaking partners, for example, POS or EtherFi. They just stake into their protocol, and they will just get the reward, the restaking reward, which is called VFHE. And the VFHE is also acts as a voting power. They use the VFHE to participate in the right side. In the right side, they use the VFHE to directly vote, to delegate, and they can also set up the voting nodes in the validation network. And in this way, the MindV will generate the voting result, and that depends on the different hub. The voting result can be used in different networks. They can be designed to generate the secured consensus for AI network, for POS network. They can put the output the result to the different networks. That's a consensus the voting result for their network. The architect is quite complicated, but the user journey is actually quite simple. The user, they just restake to become the staker, and they redeem to get the VFHE, and they just delegate to earn the rewards. And in this way, our MindV, the network, will just output the consensus result to contribute to the AI network.